drops
back out
under.
and pushes the water
Yeah,
back.
so it's a big cycle.
All right, so,
Photovoltaics.
all right.
Guys, so we've covered primary energy in Chapter 1. We covered solar thermal in Chapter 2. And remember, there are 3 modes of heat conduction. There's radiation, there's convection, and there's conduction. On that Solomon paper, what mode of heat transfer does the Earth lose heat by? Conduction, radiation, or convection?
Is what the ocean is heat by?
The Earth, the entire planet Earth. It's got to be radiation, because there's really nothing to conduct to in outer space, and there's nothing like to convect to. I mean, sure, if like the entire atmosphere was blown away, like what happens in Super Friends, or that would be the heat convecting away from the planet. But it all happens through radiation. That was something that came up from the Solomon paper. So here we have radiation coming into planet Earth, and just a second, guys, you guys are talking about meteorology. That's climate science, and the point I want to make right now, getting into photovoltaics, is that we're sort of moving from science more into engineering. So we'll see in this chapter that the photoelectric effect was first observed, 150 years ago. Einstein actually won the Nobel Prize for discovering the fact that electrons become active not by the number of photons that hit a substance, but by their frequency. He's like, well, yeah, you can pump a whole lot of photons of a given wavelength, but unless they're at the right frequency, they're not going to do their thing. And that's what solar PV is about. So moving from the science into the engineering. All right, I'm going to make this a little bit bigger. Okay. So what we're
photons per second then?
Yeah, I mean, if you have more photons per second, more amplitude, more energy at the proper frequency, then yeah, it's going to work, absolutely. Okay. Now, in its most common form, is made entirely of silicon. We're going to see why silicon is important. It's also important to note that silicon sits right below carbon on the periodic table, and there are also some photovoltaic cells made from germanium, which sits just below silicon. So remember, carbon's got those 4 bonds, so does silicon, so does germanium, and it just makes it a nice building block. It's also a semiconductor, where sometimes it's an insulator, sometimes it's a conductor, but it's somewhere in between those two. Okay, brief history. Photovoltaic, photo meaning light, and volt, which is the potential difference for an electrical circuit. And I think, Volta, he's got a little shop or lab. I think when I was there in Paris, the Volta Museum was closed. They closed those things on Monday, but it's kind of neat to see that. So here we go. Edmund Becquerel, 1839, sort of first discovered it as a scientist. Again, there wasn't really any engineering per se, but there it is. Adams and Day in 1877. Fritz, an electrician, used selenium. It's also there in that band, along with carbon and silicon. 1%, pretty low efficiency, right? Now we're seeing panels that are 20% commercially. As I mentioned, when I was at Tohoku University last February, I saw some cells that are 48% efficient. They're using quantum dots, and it's pretty wild. They'll take iron nanoparticles, coat them in ferritin, which is a protein that binds to iron, and all these little ferritin molecules turn into little balls, just like imagine dumping a bunch of basketballs on a floor. They would pack themselves. They didn't hit that whole thing with neutron beams, and the neutrons do not penetrate the iron, and so below that substrate is this little layer of balls of selenium or gallium, some element in that same band that absorbs light at a wavelength different from silicon. So right now we're looking at silicon because it's going to absorb light at a given wavelength. But imagine if you had a panel that could absorb all the light. Remember, we sort of looked at, you know, it would get kind of thick, but you know, in general, the more energetic photons would penetrate the top surfaces, but then be absorbed in the bottom layers. So that's basically what we're looking at right here. Is a little circuit. 1844 patent for a solar cell. So what you have are all these little eyes, just refer to current. Remember, I is the symbol for current. Photon comes in, they're wired up in series, typically. So when you see these solar panels around, and if you notice, like if a corner might be shaded, it's a bad thing because they're strung like Christmas lights, but just in reverse, right? The Christmas lights are pulling in electricity and emitting light. Same thing in reverse. The PV panels are pulling in light, emitting electricity, but if one of them is blocked, it doesn't conduct anymore. So, right, the whole thing, exactly. So each one of these little cells might be at like a half a volt, you know, a fraction of a volt, but then you add the voltages in series and you get a greater voltage. Greater voltage allows you to push more electrons. Okay. So here we go. Bell Labs, 1948. Barden, Britton, Shockey. And there's even, and I don't know it off the top of my head, but there is a thing, the Shockley limit, which sort of defines, if you will, the upper efficiency of this type of reaction. Okay, now this is key, right here, the process known as doping. Let me just get right into that. We're going to see it here in a little bit. Dynamic periodic table. So the key players are silicon, and the key dopers are going to be boron and phosphorus. So if we look at silicon, look at the orbitals. I like the properties too, but they're the orbitals. You can look at that 3p orbital right in the number 8, right in the middle. That 3p has 2 up electrons. There are 4 electrons missing from that, and it's those outer valence electrons that allow bonding to happen amongst all elements. So if we go to phosphorus, you can see, look, well, we filled up an additional valence electron there. It's that extra phosphorus electron that's now kind of buzzing around in the electron cloud of the semiconductor. And it's that one that's more or less, you know, it's the dollar that floats around on a Friday night or whatever, if you will. You know, it's not really in your bank. It's just, you know, you loan it to your friend, and they tip the bartender, then he went out and did something with it. It's that kind of floating dollar. You can think of it that way. Boron is the other dopant, and you can see it's missing. It's missing an electron. So that's the sort of the empty pocket, if you will, on the Friday night. Hey, put the dollar in here, I'll give it back. So that's your sort of exchange. The phosphorus has the extra electron, the boron has the extra hole. And it's actually called a hole. And so that's what allows the solar cell to. So if you've got extra phosphorus, it's extra negative. It's called N-doped. If you've got extra boron, it's sort of extra positive, and it's called P-doped. Sounds like a rap artist. Yeah, P-doped. We could get our own. We could get our own solar PV rap. What?
When is the next exam?
Today.
Exam? Today? It's
Yep.
today?
It's due
Yep.
by Tuesday.
Yeah.
Yeah, it
So,
opens today.
yeah.
Open today, it's due by Tuesday.
It's online.
Yeah.
Still getting 3 chances each month.
2 or 3. 2 or 3. 2 or 3.
2 would be reasonable.
However much torture you're willing to put into it.
Would you mind explaining the process of doping a little more? Is that just?
I think we'll see it here in a little bit.
Yeah,
it'll
okay.
come down. Yeah, it'll come down. It's very technical, and I wish they actually manufacture them. gosh, near Butte, there's a fab facility right there.
I guess the specific question is, I understand what's happening, but what's the purpose? Is it to increase the amount of photons that you can absorb, or is it, what's
The purpose is to increase the number of photons you can absorb. It's a little, oh gosh, I'm trying to just think of another analogy because, you know, at that scale, you can't see the atoms per se unless you kind of had an atomic force microscope or whatever looking at it. But the,
is it kind of creating an impermeability kind of thing?
well, in the case,
Finding the
let's
phosphorus in
think of
the
it this way. You know, if you were designing a car, right? You know, you could think of the phosphorus as sort of the seats in the car or the bus, and you could think of the space that the seat creates as the hole or the boron. So you're like, let's put a few more seats in there. Well, shoot, I put too many seats on, and now the car can't go. There's too many people in it. So there's a sweet spot there, I guess is what I'm trying to say.
Playing with bonding capabilities?
Yeah, I mean the phosphorus. We'll see a lattice structure here in a little bit, but the phosphorus and the boron do form a crystal lattice in the same way that silicon does. It's just that they're again, one's got an extra. I mean, you could even think of it as water flowing around. You know, one's got an extra drop of water, and one's got an extra bucket.
Okay, that makes sense.
Yeah. Okay, so there's the. So, kind of handy in space. Less atmosphere to deal with in space. So if you send your solar panels up, they can run electricity. So you need electricity to generate a radio wave. Okay. The efficiency of the best silicon cells have now reached 25% in standard test conditions. So, as I mentioned before, the solar constant is about 1,000. So what that is, it's 1,000 watts per square meter, and it's at a certain temperature. 130 kW. That's actually pretty good. 130 kW. That is that's 2.3 times the legal limit for a solar installation in Montana.
Really?
Well, for a net metered customer, the largest array you're allowed to have is 50 kW. So, don't park that space shuttle. I mean, if you're going commercial, I mean, if you're like, hey, we're going to become a primary production facility, you can go as big as you want. The issue there is that there's this haggling over what the cost is going to be. So you're not out competing with the fossil fuel industry. Okay, global.
Operate that on tough.
So here's the rise in total capacity, and we're seeing that more solar PV all the time. China doing pretty well. The EU is just blasting away. Yes, and that's it's for a variety of reasons. So after World War II, Germany was not allowed to have nukes anymore, right? So they're not. I think they're done digging and fracking and all that. So they either have to make it on their own, which you can see here, or import it. So there's only room for growth there in North America. Now, this price is, I mean, it's recent, but it's ancient. The price per watt is 41 cents now. It's a fifth of what you see right there. So it has just plummeted in the last 7 years. It's 41 cents a watt. So up from $10 a watt, 41 cents to make this stuff. Okay, here's standard test conditions. And the idea is that you have a certain air mass. So if the sun is directly above, you've got the length, OZ of air, but as the sun sets or as it's rising, the amount of air that the poor photon has to get through. Remember the traffic jam in the sun? I mean, it took that photon 9 million years to get out of the core to the surface, 8 minutes to get here, and then it hits the atmosphere. Well, again, there's some traffic, a little bit of molecular traffic jam between the top of the atmosphere and the surface. So this is the air mass 1 is that equation right there, 1 over the cosine of theta. So
you could think about the gases in Earth's atmosphere as sort of the proponent for a longer period of traffic jam in Earth's atmosphere.
yeah, that's what they are. Yeah, that's exactly what they are. And greenhouse gases make the traffic jam that much worse, or better, because you need greenhouse gases. That's the number right there, the 1365 at the top of the atmosphere.
And we lose about a quarter by the time it's on the ground.
Yeah, maybe. Yeah, in general. But like I said, I've stood out back behind East Campus, put a gauge out, and I've seen 1400 before because of lensing around clouds, but just briefly. It just kind of comes and goes. So the word we want to think about there is attenuate rather than traffic jam. The gases are attenuating different frequencies. So air mass 1.5 corresponds to the spectral power distribution observed when the sun's radiation is coming in from an angle of about 48 degrees. It just means you've got about 50% more atmosphere in the way than you would if the sun were directly overhead. So this green line at the top, that is the Stefan-Boltzmann equation for radiation of a black body. It's 6,000 K, which the sun is. It's a fourth order equation. If you notice, and you saw this in summary 3. So remember when we did our parabola, our quadratic, it had one bend in it. It had a single minimum or a single maximum. This curve, that green curve, has 3 bends in it. It's bending up right here, it's bending down right there, and it's bending back up again. So if that equation were just a line, and you asked this question earlier, Rob, about could we graph these equations as lines? Yeah, and they're just lines. They don't have any curve at all. It's just you start here and you go up there. If you throw an exponential at it, it's got a bend. The bend.
Polynomial equation.
Exponential is not a polynomial. I mean, you could approximate an exponential with a polynomial, but an exponential is an exponential, and it's always going to bend either up or down, but not neither and not both.
But the product of that line in particular has 3 different equations attributing to the bends.
This guy, 3 different equations? No, one equation with multiple bends in it.
Okay.
Yeah, so if you had a fourth order polynomial, it'd be one equation, but you'd have 3 bends in it.
Gotcha.
So my point is, it's fourth order. So the distribution of energy goes by the 4th power of temperature. We can dig into why that might be, but that's just how it is. It's and that's why the curve looks that way. It's got 3 bends in it. 'Cause it's a fourth order equation.
Power is fourth order.
Temperature. Yep. That's exactly right. So here's air mass 0. So that's right at the very top of the atmosphere. This is air mass 1.5, and these little valleys are, of course, the absorption or attenuation by molecular species in the atmosphere. So this is basically what we have to work with, and that's on the ground, on the Earth's surface. And again, that's that 1,000 watts per square meter that we just use every day. So, okay, so here's the PV effects in crystalline, basic principles of doping. So So as I said a second ago, there are p-type and there are n-type semiconductors depending on what is doped. And as I was saying before, that dollar that was floating around, those are the free electrons. Those are the electrons that are sitting out in the outer orbitals of the semiconductor. You know, in a car is actually a pretty good example. So, and you could even think about this. Parking's not that bad in Missoula, but let's say you know, there's a parking ordinance, and you know, no street parking in this residential block between 8 a.m. and 5 p.m. Well, when that 8 a.m. whistle blows, energy isn't being injected because here comes the police. I better get my car out of the lot and up into the conduction band. Well, in a PV cell, it's just like, here comes the sunshine, and that's what kicks the electron up into the conduction band.
Kind of
And
like photosynthesis a little bit.
Yeah, it's a little bit like, it's a lot like photosynthesis actually. So when that electron comes in, there's a lot more going on in photosystem 1, and we'll look at that in chapter 4. But yeah, it's the photon comes in, kind of rattles the cage, if you will, of that lattice, and the least bound electron sort of pops into action. It says, here I go. And if there's a load, you know, if you've got a anode and a cathode somewhere, ready for that, away it goes.
Do you think the original design from solar panels came from photosynthesis plants?
No, it did not. So the question is whether or not original design for PV panels came from plants or not. And in the same way that we typically don't build airplanes that have flapping wings, you know, birds, bees, whatever, will flap their wings. And I mean, sure, you have a photon coming in and hitting matter, but yeah, kind of different beasts.
Right.
Yeah.
Gotcha.
Yeah.
I just meant something that nature has basically mastered over a millennia. Just how they're shaped to take in as much sunlight as possible, especially given the fact that they're competing against other plants for that.
Yeah.
I think that you could learn a few things.
Yeah, it's a good question, and they're actually the Naval Research Lab in D.C. does have an organic PV division. There's also one at Idaho National Labs, organic PV, where you're just using organic, carbon-based molecules. There's a technique for tethering gold to the sulfur ion that's sitting in photosystem 1 to pick that up. So I mean, people are working, but that's more like a reverse engineering problem, whereas making PV has been more or less a forward engineering problem.
Right.
Yeah. Okay. So there's the photons. We know there's 310. So you can think of the car as being the electron, and now here's the hole, and it actually allows for flow to happen. So there's there are actually new cars sort of coming in all the time and being bounced through this. It says the sleeves bind a hole that carries them on the ground floor to move around. So it's just a good analogy of what's going on there at the molecular scale. Okay, so to look at the lattice itself, each one of these little lines is a photon coming in, and okay, here we go. So this is just silicon. So you can see if we come in, let's make sure we get these right. There's A, B, and C. So B has phosphorus in it. Each phosphorus atom shown in green has 5 valence electrons. Not all of them are taken up in the lattice, and that's the N. So that extra electron causes the N, or the negative. And in C, that's boron. So let's look at the difference between those two. And I think that'll answer that question you had there, Kat. So the top is just regular old silicon. Here we have phosphorus, and you can see that little electron that wasn't there is now there. It's completed by that 5th electron in the phosphorus. And then I think we should see the same thing between A and B. Yeah, so see that little missing electron there? Well, put your phosphorus in and now the electron's there.
So we're representing a missing electron by making it blue instead of red on the diagram.
Well, so the top is just pure silicon
Yeah.
everywhere. And what we're showing here, there's sort of a conservation between like the photon coming in and an electron going somewhere else.
Mhm.
So in this
It's
case,
representing a little red
yeah,
area.
so in this case,
Okay.
this electron sort of left the lattice and there, here comes a photon, et cetera, et cetera. In this case, the phosphorus comes in, 1, 2, 3, and let's see, I thought it was a 1-to-1 ratio. You can see the missing one there, the missing one there. This guy, it's like, where's Waldo? I don't see the missing one there that phosphorus filled in, but that's what they're trying to show.
Because it shows like electrons still leaving, you know what I mean, but it fills in with what the phosphorus has. Or is that meant to be a photon? What is that little red arrow?
The red arrow is a photon. Yeah.
Okay, I see.
It just might be a little typo, but.
Yeah, that makes sense.
Okay, but you can see where now where the boron comes in, you've got these sort of extra holes. 1, 2, 3. So you put the boron in, and there's just not an electron there because the boron didn't have one to start with. Okay, and here's the structure. So you need a path for the electrons. So you've got a conductor on the top. You've got a conductor on the bottom, and what we're seeing here, there's sort of multiple things that can happen to that electron. So it could come in and just bounce off, and these panels get better all the time where these contacts become thinner and thinner, and you'll see them. Those are little stripes right on the so if they're big and thick, you're going to lose some of those photons to reflection. They could just go all the way through. Whoops. Well, can't win them all. And then and you can see in the case of photon 1, let's just look at the distinction between photon 1 and 2. Okay, so in 1, it dislodges one of the electrons, which leaves behind a hole. The energy required to promote the electron into the conduction band is known as the band gap, and we'll talk about that here in a second. The electron thus promoted tends to migrate into the layer of N-type, and the hole tends to migrate to the P-type. The electron then travels to a current collector on the front surface. So that's what's going on here with photon number 1. Comes in here, smacks an electron, and this electron-hole pair is formed. It's sort of like the seat and the empty seat. All of a sudden there's a new bench on the bus with a place to sit. One goes, when the photon comes in, the electron goes somewhere, and now there's a hole there for a new electron to come in. Yeah, yeah.
Just imagine a bus filling up to the brim, and people are left standing when it takes off, they fly out the back or something. I mean, that's part of what this is like. There's only so much room for the electrons and the photons.
Yeah, that's what I was thinking, is that it's basically to make room so you don't lose electrons.
Yeah.
During the process.
Yeah.
Okay.
Yeah. Now, read this little bit. It says, if a photon with an amount of energy greater than the band gap strikes the silicon atom, it again gives rise to an electron hole pair, and then the excess energy is converted to heat. So you don't actually get your electrical conduction if this happens at 2. It doesn't actually migrate. This photon or this electron does not actually migrate all the way down, and you just kind of heat the thing. It came in with too much energy. But at the end of the day, as these electrons, and so the electrons themselves, and here's the other kind of strange thing to think about, is to get a current, every single electron doesn't have to go all the way around the circuit. It's very similar to the fact that right now while I'm talking, I'm making pressure waves, but like the air near my mouth is not actually going into your ear. Like It's just a wave. It's just a wave. And so the same way, and you can think of it, you can think of this thing as the same as like a traffic jam of electrons where, hey, I want to get the front car moving and I'm in the back. I just bash the guy's bumper in front of me on up the road, and then the signal goes. So it's a little bit like that. I mean, the electrons are moving, but they're not propagating at the speed of light, which is in fact the rate at which the electricity flows. Just as, you know, if I put a little wind gauge in front of my mouth right now, I might be talking at mile per hour, 1 or 2 miles per hour of wind, but the propagation of the acoustic signal is happening at whatever, 500 or 700 feet per second.
So
Yeah.
you're saying that the electricity is moving faster than the electrons?
The electricity is moving faster than the electrons. It's a great way to put it. Yes, yes, yes. The electricity is
So
moving
you get
faster.
kind of a buildup like in the actual solar panel.
I don't know if it's, I wouldn't call it a buildup any more than like there's a buildup of energy. Like, you know, every time I speak, there's not really a buildup. I mean, the wave kind of dissipates and it's still here somewhere, but it's always moving.
So
You know?
that's the reason why the boron and the phosphorus are important, because it helps accelerate the generation of electricity.
Yeah. You could think of the boron as extra parking spaces. You know, if you want to drive in the parking lane for a while, and the phosphorus is like an extra lane.
Gotcha.
Yeah.
For electrons.
For electrons. Yeah.
Okay.
Yeah. Yeah. Okay, and that's kind of a tough one, because we don't typically think of matter that way, but it is. Okay, so I mentioned the electron-hole pair are generated, and that's what allows the electricity to move. And again, the holes can be thought of as floating upwards, moving upwards, and the electrons floating downwards in opposite directions. Okay. So how are we doing on time? I guess we're okay. Okay. So the conduction band is, and again, if we sort of go back to the periodic table, you can sort of think of these upper levels as the conduction band. The electron hasn't actually left the material. I mean, if you charge it enough, yeah, electrons will fly right out of that thing. And that's how old CRT TVs used to work, because you're actually shooting electrons at the front of the tube. But well, it's real, it's true. But in this case, the electrons, they stay in the silicon where they belong. But up here, it's higher energy, and that's the so-called conduction band. The valence band is lower. That's sort of your bank of the electrons that are closer. So when that photon comes in, the electron moves out of its parking space, out into traffic, and now it rolls. But as it's used up in an electrical circuit, it comes back down. So if you get a lot of, think of it with a lot of different holes, as the photon comes in, that electron is sort of shot up into the conduction band, and the hole so-called floats up a little bit from the N, from the phosphorus. Remember, the phosphorus is where the electrons are hanging out, up into the P where the boron is.
It's like the ocean currents we were talking about.
A little bit, yeah. You can just think of it as a cycle flowing. Yeah, you can think of it as a cycle. Yeah, yeah. All right. Let's just do a little bit more on the tech. So, monocrystalline, and I wish I'd taken a picture of it yesterday, because I was under the what bridge was it? I was either under the Orange Street. I was under the Orange Street Bridge, and there were all these fantastic crystals of ice, just like, how did they make, what the, it's like all these wacky shapes, and it was obvious that those crystals took a long time to grow. If you just go out and like flash freeze water, it'll be a clump, but if you sort of allow that crystal a long time to grow, get some fantastic shapes. So in a monocrystalline cell, you just got one giant single crystal of silicon. And the Choralski process, we'll see that here in a little bit, as well as the epitaxial process we'll see here in a little bit, actually is responsible for single crystal silicon.
This is a seed crystal?
Yep, seed crystal. Yeah, in the same way the little seed.
Those you little kid packs where you can.
You think of it the kid pack, yeah, where you put it in the water and you leave it in overnight, and then the next morning here comes the giant crystal. Yeah, it sort of sets up. It's not unlike if you're going to go build a building, you lay your foundation, and then you look, oh my gosh, a building just grew, and all of the bricks are in this neat little lattice. Very similar, except it just happens through self-assembly at the small scale. Yeah. So we start, here's nature, sand, silicon dioxide, and that oxygen's got to go, and the only way to get that oxygen off of there is to cook it, is to heat it in a vacuum, so the oxygen burns off, I guess, for lack of a better word. From there, we go into HCl. So remember, we're actually looking for single silicon atoms. And so we're going from this natural crystal to single atoms. So HCl, and now the chlorine is going to bind with the silicon. So now we've got chlorine over here binding with the silicon. Remember, chlorine just has that one, see that one little missing valence? So it's going to bond really nicely with the silicon, and each one of those ones is going to stick in there. So you can imagine SiCl4 happening in that little bath. So high purity trichlorosilane. So in this case, there's going to be 3 chlorines attached to it. Reduction with hydrogen. Now we're at 900 C. The H2, the H comes in. Here's hydrogen coming in. So it's just got that one electron sitting out there. Here's chlorine. So that one little electron sneaks right in there. HCl, party time, And then you're left with that almost pure crystal silicon. So then it's grown into this crystal, which I would love to see someday. I'm sure there's plenty of cool YouTube videos on there.
So sand and glass, that's a huge process.
Yeah.
We have to know this on
It'll talk about the Choralski. You'll see it. Yeah.
This is kind of how they make glass too.
I don't think glass is this sophisticated. I mean, some of it might be. But glass is more just like melt the sand, lay it flat, let it dry, stick it up. Yeah, I think it's a little less involved. You don't need the crystal properties here in order to get this. So slice it, saw it, polish it, dope it, and that's going to happen in a vacuum. And again, you're just firing in boron or phosphorus gas. Anti-reflection coating, contacts for the conductors, put them into modules, ship it, test it, go solar. Yes.
When they dope the silicone wafer, you said they just blast it with the boron or phosphorus gas?
Pretty much, yeah.
Wow.
Yeah,
And
yeah.
just because of the electron, like the missing electrons and the electron, like they can bond that way, just the gas with the
Yeah,
crystal?
that's a good question. I wish I knew a little bit more about it, but the if those phosphorus and boron atoms, and then in this case they are coming in. And you could imagine, because they can come in as ions. So in the same way I just mentioned, you could, we fire electrons at a tube to make pictures, and that's how the CRTs work. You're just firing boron or phosphorus at these things at a certain rate, and they just go in and kick them out. Yeah. There's a little more to it than that, but that's the basic idea. They weren't there before. We fire them in, sort of electroballistically, and then they're there. All right, let's take a little break. It's a lot.
So it's kind of like